All right, so welcome everyone to the second block of HMMT education. My name is Andrew. I'm one of the organizers of HMMT education this year. And we're really excited that you're joining us with Professor Sipser here for our second block. As a general ground rule reminder, be respectful of Professor Sipser's time and try to use the Q&A to ask any questions you might have during the event. As always, we reserve the right to kick people who are being disruptive, so please don't make us have to do that. But I want to make sure to give as much time to Professor Sipser to present as much as possible, so I'll just quickly do an introduction. So Professor Sipser is the Donner Professor of Mathematics and a member of the Computer Science and Artificial Intelligence Lab at MIT. He served as a Dean of Science from 2014 to 2020, and his research areas are in algorithms and complexity theory, specifically efficient error correcting codes, and various other topics. If you'd like a full introduction to Professor Sipser, you can check out the HMMT catalog. With that, I'll hand it over to Professor Sipser. Thank you so much for joining us today.
Great, thank you, Andrew. And thank you all for being here. I am going to talk to you today about a problem that's in the intersection between mathematics and computer science. In a field that's called complexity theory, and that's part of a broader field called theoretical computer science. My talk is not going to need any background. I think you can pretty much understand it from just your general knowledge. And it's not a very intensive or particularly deep talk. It's about a problem called the P versus NP question, which I'm sure many of you have heard of at this point. If you feel you already know everything about the P versus NP question, then this may not be the right talk for you. You can check out one of the other parallel talks that are going on, because this is going to be pretty much a somewhat light introduction. But with that, let me jump right in and set the scene with a very simple example. And that's going to be just a problem we call multiplication, 7 times 13. And the answer, as we all can figure out pretty quickly, is 91. And I'm also going to talk about the reverse of the multiplication problem, which is if I give you the number 91, and I'd like to know what are the factors that produce that, that multiply together to give you that number, we call that the factoring problem. So that's kind of, the factoring problem is sort of the reverse of the multiplication problem. So those were very small, simple examples that you could do in your head. I'll give you a little bit of a bigger one, which you probably won't be able to do in your head, at least if you're a normal human being. If you take these two larger numbers, you can multiply them together. But now you would probably want to use a computer because if you just type those numbers into a computer and you push multiply, assuming you have the appropriate software which can handle a large integer multiplication of that kind, then the answer will come out, which is the number in red. And that what's interesting is that that answer will come out very quickly. It'll just really take the computer less than a second to come up with that product. And that's just because the computer would follow the same procedure that you learn to, that you use to multiply numbers and that you learned when you were in grade school. But it can do it just much faster than you can do it because of, computers are pretty fast. But interestingly, if you look at the factoring problem for numbers of that kind, so let's say if we take that product now, this number which is has something over 100 digits, and I give you that's now your starting point, and you didn't have a chance to write down those two factors from that previous slide, so now you need to figure out what they are. You could do that again. Probably you'd want to use a computer And in fact, it has been done. Somebody actually went through the exercise of starting with that number, coming up now with the answer, which is the product of these two numbers, which multiply together to give you that that product. And but here is the difference. Whereas the multiplication of the two numbers in red to give you the number in blue took a second of computer time, the factoring problem of starting with the blue number and producing the two numbers in red, that took much longer. In fact, it took, we know because someone went through the effort of doing it. It took 33 computer years of effort. Of course, we didn't really wait 33 years. This was done on a parallel computer back in 2005. Someone actually did that calculation back in 2005. And it was on a parallel computer with 80 processors, but it still took 5 months for that 80 processor parallel computer to come up with that factorization. Now, why in the world would someone spend so much effort to find that that factorization? For one thing, they got paid $20,000. They actually got $20,000 for doing that factorization. And you might think then, well, that's pretty cool. Why in the world is someone paying $20,000 to factor numbers? That's question number one. And question number two is, how can we get a piece of that action? Well, if you're interested in payments for factoring numbers, here's a number which is a $100,000 number, and that number is a bit larger, has somewhat more digits, and no one knows the factorization of this number. We do know it's a composite number. It's not a prime number. It does have a factorization, but no one knows what it is. Now, before you get too excited and start to work on it, and expecting to get that $100,000 bounty for factoring this number, you should know that the people who are offering that money for the factorization have stopped the award, so they're no longer paying for factoring numbers. So don't come to me complaining if you factor the number and you're looking for the payment. But mathematicians are still quite interested in algorithms for factoring large numbers for a variety of reasons. For one thing, it's just interesting from a mathematical standpoint. Mathematicians, of course, have been interested in prime numbers for hundreds of years, and the problem and factoring numbers was a problem of interest to them for a very long time, going back for hundreds of years. So mathematicians are just interested in the problem. So they're basically doing it kind of maybe not for fun, but because they're interested in it. But as many of you I'm sure know, there is a connection between factoring, the factoring problem, and the problem of communicating securely, say over the internet. Because there are cryptographic schemes that depend on their security for the difficulty of factoring numbers, in the sense that if you find a fast way of factoring numbers, you will break the security of those crypto systems. One of them is notably the RSA crypto system, and the RSA people were the ones who originally offered the prizes for coming up with factorization. I think largely, I don't know for a fact this is true, but I think largely because back in those days, they were trying to keep tabs on the progress that people were making in coming up with factoring algorithms. So they were back then paying these prizes, and that the RSA factoring challenge stopped something in around 2007 or so. But these numbers are still around, and they serve as challenges for the computational number theory community to see how well they can do at factoring. And incidentally, people are still working on these problems. This number that I have up there has 309 digits. Pretty much the state of the art is around factoring 250 digit numbers. And there was a 250 digit number factored just this year using the latest algorithms for factoring and high powered computational resources. So but from a theoretical standpoint, what is it about factoring that is so hard? The problem is that as opposed to multiplication, to find factors, in multiplication, you can kind of construct the answer. If I give you two numbers to multiply, there's a procedure which actually builds the solution out of the starting point. In the case of factoring, really kind of no one knows of a constructive way of coming up with the factors. The only thing that you can really do is try all possible candidate factors one by one and use trial and error, keep dividing, all the possible candidates until you find one that works. And when you have large numbers, such as the numbers I was just showing you, which have hundreds of digits, then that brute force search approach is going to be very slow because the space of candidates is so enormous. Now, the kind of question that I am interested in, and many of the people in my community are interested in, is whether that searching is really necessary, or whether there's a more direct, constructive approach for factoring numbers, which can avoid the search. And the answer to that is, despite a lot of people thinking about it, is we just don't know whether there is a fast way of factoring large numbers. Okay, so this is a very famous unsolved problem in theoretical computer science and complexity theory. Let me turn to a different looking problem, but which still has a very similar character. And that's called the CLIQUE problem. The CLIQUE problem, which I think our previous speaker also was talking about cliques in the context of Ramsey theory, but I'm going to talk about it in the context of algorithmically trying to find cliques. So here, a clique is going to be a connection of nodes in this graph, which are all connected to one another. So this would be a 3-clique, a 4-clique, and 5-clique, and so on. So you're looking at finding cliques that sit within this graph. So here is a 3-clique. These 3 nodes here would be a 3-clique, and these 4 nodes over here, these 1, 2, 3, 4, these would be a 4-clique. So my question is there a 5-clique in this graph? And you can imagine that might actually take you a little bit of effort to figure out. But, in fact, there is one. Here it is. These 5 nodes form a 5-clique. And if you want to see it more clearly, I'll just darken up the edges to see that there, in fact, is a 5-clique sitting inside this graph. But now if I give you a somewhat larger graph, and I want to know, say, is there an 8-clique in that graph? Well, now it's going to take you a while. You can just try you can try going through the subsets of the nodes one after another of the size of clique you're looking for, but that's going to start to take a long time. And in fact, if we're talking about graphs that have hundreds of nodes, and you want to try to see, is there a clique of size 50 or 100, in a graph that has, say, 500 nodes, that could take a very, very long time. And we don't have algorithms which can do essentially better than the brute force search approach. That's, again, it's like factoring, that the only way we know how to solve this problem is by searching for the answer. Now, again, the question for a complexity theorist is, well, can we avoid that searching somehow? Or do you really need to search? And again, we don't know. Very fundamental problem. So both of those problems and many others are what one might call needle in the haystack problems, where, somewhere there is buried within a large space of possibilities, there is this needle, this thing you're looking for. But the set of and when you find it, you got it. But looking for it might take you a long time, because It's such a large search space. And the question is, do you need to search, or can you somehow avoid searching for these problems? So taking the same thing slightly more abstractly, you want to know, do you need to search to find the needle? Well, in some cases, from a physical standpoint, maybe you don't need to search. If you have a magnet and the needle is magnetized, you can just pull that needle right out without actually going through the search. And for these other problems like CLIQUE and factoring, what we're really asking is, can there be a mathematical analog to the magnet? Something that will just extract out that solution without having to search through possibilities to find it. But, as I say, this is a problem in the field that a very fundamental problem that we just don't know the answer to. So it's a phenomenon that's very widespread. It appears in many, many other problems. Have this kind of can be solved by searching for the answer, but where we don't know whether searching is necessary. So the problem, for example, you have a set of tasks that need to be scheduled, in a factory or on a processor or something like that, scheduling exams in a university. And you want to find a schedule that has a limited number of conflicts, say, for the final exam schedule. Or you want to find a way of coloring a map that only uses a certain number of colors. You're given a mathematical statement. You want to know, is there a proof of a certain length? Many of these problems, these are all examples of problems where they can be solved in principle, but solving them as we currently understand them can only be done by searching, and we don't know if there's a way to do better. So that is really the essence of this problem we call the P versus NP question. Can we solve search problems without searching, or is sometimes searching necessary? So just to explain that terminology, if you haven't seen it before, let's see, there was one question. Does an NP problem tend to have a P inverse? Because of like the multiplication problem I gave you, the factoring problem has a the polynomial time inverse of multiplication. I don't think you can say a general thing like that. Okay. I'm not sure I'm supposed to be taking these questions as we're going, but anyway, that's you can give me guidance on that, Andrew. But anyway, okay, getting back to P and NP. So the P problems are the ones that you can solve quickly, kind of like multiplication, without being too formal about it. These are the things that you can solve that way you don't need to search. Whereas what we call NP problems, or non-deterministic polynomial problems, those are the problems where you might be able to check, you can check the answer easily once you find it. Like once you have a clique of a size that is your target, you can actually check that the clique is there and it works. Or if you're looking for factors, you can actually check that the factors multiply together to give you the answer. But it's just finding that clique and finding that those factors. That's what seems to be hard. So finding the answer is hard. Checking the answer is easy. That's the essence of these so-called NP problems. And represented kind of diagrammatically with a Venn diagram, the NP problems include the P problems, because anything where you can find the answer quickly, you can certainly check the answer quickly. But there are problems for which we know we can check the answer quickly, like factoring, where we don't know whether you can find the answer quickly. We just don't know. Once we've formalized this notion of P and NP, then the P versus NP question becomes a precise mathematical question of whether these two classes coincide, whether they're the same class, or whether they're the different class. So if P was different from NP, that means that there are some problems that really need searching, because these two classes would be different. Whereas if P were equal to NP, that means that any problem where you can check the answer quickly, you can also find the answer quickly, which would be kind of amazing if that were true. And most people, in fact, believe it's not true. Most people believe that P and NP are different, but it remains an open question. So turning a little bit to the history of P versus NP, I'll be very brief about it, but there's an interesting part of that history. It really got its started in the 1960s when people were starting to formalize, how much time it takes to solve problems and things of that sort. The problem P versus NP question itself was first formulated in the literature in 1971, but kind of amazingly, as was discovered in the archives of von Neumann, Kurt Gödel had written a letter to von Neumann, which kind of laid out the P versus NP question way back in 1956, really pretty much before anybody was thinking along those lines. So it's kind of an amazing letter that was discovered in von Neumann. And I think it's an amazing discovery that this letter exists. So just to show it to you, since I kind of love this letter. Here it is. Well, I'm not going to go through it in detail. For one thing, it's in German, and I don't know German. And also I'm going to translate a couple of little bits and pieces of it, just to make sure you're familiar with the two characters here. Kurt Gödel was, the greatest logician of the 20th century. He's famous for having shown that there are, for example, unprovable statements in mathematical systems like number theory or set theory. There's always going to be things that there are statements that are going to be true, but for which you cannot prove that they're true. They're just undecidable from the axioms. So that was part of the work that he had done in the 1930s. And the other person I mentioned is John von Neumann. He's was a very broad applied mathematician, worked also in lots of branches of pure mathematics, and he's was one of the people who built one of the earliest computers. In fact, he's even the architecture that we use is often called the von Neumann architecture for storing the program of the computer in the memory of the computer. Without getting into that, let's just look at this letter that Gödel had written to von Neumann. So he starts out saying, Dear Mr. von Neumann, this is the date of the letter. Curiously, both of them were working in the same place at that time, at the Institute for Advanced Study at Princeton. And I imagine their offices were down the hall from one another. So it was kind of, you might think it's strange that Gödel would be writing a letter with this question to von Neumann instead of just knocking on his door. But it was at that time Gödel himself was a very shy person, and maybe that was the way he felt most comfortable communicating. But it was also possible that, and I don't know the exact history here, von Neumann, I know, was ill with cancer at the time, and in fact, he lived only about a year longer than this, and so he may not have been coming into work because of his health. And in fact, Gödel refers to von Neumann's health in the very first page of this letter. But then he says, but let me turn to an interesting mathematical problem. And the mathematical problem is, I'll just describe it very briefly. One of the things that came out of Gödel's work in the 1930s is that there is no algorithm which can test whether a mathematical statement has a proof. You just can't tell. You can't say, given that statement, and feed that into an algorithm, and the algorithm is going to say yes or no, that statement has a proof or it doesn't have a proof. A little different than testing whether it's true or not. It's just whether it's provable or not. But if instead of asking whether it has a proof at all, if you want to know, does it have a proof of a certain length, say with a certain number of characters in it, well, then that certainly becomes, assuming we have everything formalized as logicians know how to do. If you want to know, is there a proof of a certain, with 10,000 characters? Well, now that is a algorithmically solvable problem, because you can simply try all possible proofs of 10,000 characters and see if any of them actually are legal proofs of the statement that you're trying to prove. So now it becomes a decidable, solvable problem algorithmically, but so computer could solve it. But the question is, now this becomes one of these searching problems, because there is a lot of possible proofs that you would have to look through to test whether there's a proof of the given length. And so Gödel is asking, he exactly lays it out just as I laid it out to you, a little bit more succinctly in this letter. And then he goes on to say, suppose we take this question, the problem of testing if there is a proof of a certain length, and we say, how fast can we tell, let's say, if there is a proof of length n on the fastest possible machine? So this would be the phi of n is the running time of the machine on the optimal machine for testing, is there a proof of length n? That's really the P versus NP question. You want to know, does that n grow, does it grow exponentially or does it grow polynomially? Does that phi of n function? And he goes on, talks about exhaustive search. He talks about problems like testing if there's a number is prime and other combinatorial problems, and then goes on to sign the letter Kurt Gödel. So this is really an amazing bit of history in the history of science. So since that time, the P versus NP question has become very famous. It's one of the 7 millennial problems that were put forward, sort of patterned after the Hilbert problems from 1900. This was done in the year 2000. These were 7 problems put together by a committee of mathematicians as grand challenge problems for the mathematical community for the coming century. As you can see, P versus NP is on that list. In fact, one of those problems, the Poincare conjecture, has been solved already. One difference, I mentioned the Hilbert problems, one difference between these Millennium problems and the Hilbert problems is that for these Millennium problems, there is there's a prize for solving any of them of $1 million that was put forward by this fellow Clay. That's why they're called the Clay Millennium problems, because of this prize money that has been put forward. But many people are just interested in this problem anyway, just because it's a fascinating problem. And because I've been interested in this problem for a long time, people sometimes write to me with proposed solutions for proving P different from NP or proving P not equal to NP. And the kind of thing that's tempting, and that actually a lot of people fall into, is that they feel it's sort of obvious, because there's kind of, what else are you going to do for solving the CLIQUE problem besides looking for the CLIQUE? And then, but that's the whole point. There might be something more clever. And I want to try to illustrate that with the case of primality testing, where you might think that for testing if a number is prime, what you need to do is you need to try all possible factors in order to test whether a number is prime or not. But there are other methods for testing if a number is prime. And a method that I'm going to mention to you, just to illustrate that, is a method that relies on something called Fermat's little theorem. It's an old theorem due to Fermat, not his famous Fermat's last theorem, but this is a theorem that Fermat did prove. And it's just simply that if you have a prime p, so you take any prime number p, and a number a that runs from 1 to p minus 1, so a number a that's less than p, and you raise a to the p minus 1 power, and you divide by p and take the remainder. That's what this means. This is it's congruent to 1. So if that's the remainder after dividing by p. You always get 1. So let me show you that by example. I think this will, if you didn't understand what I just said, the example will make it clear. So you take p, your prime number, let's say 7, and take a less than p, let's say 2. So the calculation is not too hard. And so now you're going to raise a to the p minus 1 power. So that's 2 to the 7 minus 1, or 6 power. So that's 64. Now you divide by 7 and take the remainder. Well, we know 7 divides evenly into 63, so the remainder is 1. And that's consistent as it needs to be, because this is a proved fact here. That's consistent with, as an example of Fermat's little theorem, that you're always going to get 1, no matter what p you choose and what a you choose. You're always going to get 1 as the remainder. It's kind of amazing if you actually try to do those calculations, that you always get 1 that comes out. And just to illustrate, it doesn't always hold if you start with a number that's not prime. So let's take 15, take a equal to 2 again. Now you raise 2 to the 15 minus 1, or 14, you get this number here. You divide by 15, take the remainder. Well, now the remainder is 4, which is not 1. Now what's interesting here is that that little calculation is a proof that 15 is not prime. But that proof doesn't tell you anything about the factors. It just proves that 15 is not prime because it doesn't have a property that we know all prime numbers have, but it doesn't rely on finding the factorization of 15 to show you that it's not prime. Anyway, so this can actually lead to a faster algorithm that avoids searching. You know, I mean, there's a kind of a whole story, which I'm not going to get into, about primality testing and algorithms, but you know, you can basically, we now know how to solve test if numbers are prime without doing, significant searching. One of the main advances toward the P versus NP question came shortly after it was formulated, around the same time it was formulated, and that was this notion of NP completeness. And let me illustrate that again by taking an example. What the notion of NP completeness tells you is that there is a connection between the difficulty of solving certain problems and the difficulty of solving other problems. Their complexities are related. So specifically for the examples that we showed earlier, if somebody finds a way to solve the CLIQUE problem without searching, so solve the CLIQUE problem quickly, then they can use that to factor numbers quickly. Which, if you think about that for a second, that's kind of amazing right there, because the factoring problem seems like it has nothing to do with the CLIQUE problem. But if you can solve CLIQUE quickly, you can factor quickly. And that's because of this notion of a transformer. There is a way that's been demonstrated for converting factoring problems into CLIQUE problems. So I'll kind of show it here. Here's your factoring problem. You feed it into the transformer does some calculation and produces a CLIQUE problem, which embeds that factoring problem inside it. In such a way that if you find the CLIQUE, that's actually going to show you the factors. And you can do that with any NP problem. So that tells you that if you can solve that one problem, the CLIQUE problem, in polynomial time, then you can solve all of the NP problems in polynomial time. That's what the notion of NP completeness is about. Now, I just want to mention that there are problems that kind of go beyond NP as well. So complexity theorists, so moving on to sort of the broader question of complexity, there are problems that seem to be beyond NP in the sense that you can solve them by searching, but no one knows whether there's a fast way of checking the answer. So if you take, for example, if a game like chess, and you want to know, given a chess position, for example, maybe the standard initial position or some other configuration on the board, which side is guaranteed to win if both sides play optimal. Well, for example, in this configuration here, we don't know. Does white have a forced win, or maybe black has a forced win, or is it a forced draw if they both play as best possible? Now, you could solve that in principle with a computer. I mean, you can solve that in principle, with an algorithm by writing out the entire tree of possible chess games, and then analyzing that tree to determine which side has a forced win, or whether it ends up being a draw. But that tree is larger than the number of atoms in the universe. It's astronomically large, and searching it would take more seconds than there are, than we believe that the amount of length until the universe goes cold. But so it would take a long time to search. It's a huge search space. But even if someone somehow did search and figured out the answer, there's no easy way of checking that answer is right. So it's kind of, in a way, a searching problem that kind of goes beyond NP. But we have there is a classification system that complexity theorists have come up with. If you were interested in studying this a little bit more advanced, there is these classes P and NP, but this games problem like chess or other related problems, that's in a class called P space. And there are a variety of other complexity classes that have been investigated over the years, which kind of naturally sort of correspond to the complexity of various problems. So let me just jump on here. So I'm beginning to run short on time. The problem of solving P versus NP, or proving P different from NP, which is what most people would bet is the answer. So how might one go about doing that? Well, one approach that many people have thought about, which is a typical problem in typical way to go about attacking hard mathematical problems, is you try to find, you ask, is there perhaps an easier problem that's in the same spirit as the hard problem you're trying to solve? So in the case of P versus NP, that easier problem might be, where you're trying to show, you take some problem, you take like the CLIQUE problem, and you believe that the CLIQUE problem really is going to take a long time to solve on your computer. But how do you prove that? So one of the things you can do is, the challenge here is that, the reason why this is hard to address is because the algorithms can be very clever. The class of fast algorithms is a very rich class. And so somehow showing that none of them can work is beyond our understanding of how to do it right now. So what you perhaps can do, so I think of the algorithms as like the devil. So what you can do is you can kind of restrict the class of algorithms that you're going to look at. You can think of that as handicapping the computer. So it can't take full advantage of the computer's power. It's kind of limited. So it's a handicap model of computation. So you've kind of think of it, you hit the machine, broke its leg, so it can't run anymore. It can only limp. And now maybe for this limping computer, you can prove that the CLIQUE problem is going to take a long time to solve. And if that doesn't work, you kind of whack it again, you break both legs, now it can only crawl. And eventually, if you limit the computer enough, you can actually show that the CLIQUE problem is going to take a long time to solve. And then hopefully, maybe you can then relax some of those constraints, because maybe you learn something and show for more and more powerful models that the clique problem is going to be hard to solve. Well, I mean, that's an approach that many number of folks have taken. It hasn't gotten us to where we want to be yet. So another idea that people have had is to say, well, let's try to find hard instances, hard clique problems. And that sort of leads you right away to thinking about, well, it's probably a good idea to look at larger inputs, larger graphs, because that's where you're going to see quantitatively a bigger and bigger difference between what a fast algorithm can do and what would be required if what happens when you need to search. And so taking that to its extreme, it suggests that it might make sense to look at even infinite inputs, if you could make sense of that. And there are some ways that people have made some sense of that. So you take infinite inputs where you want to know, then if you can make sense of that, perhaps there the problem of whether you can sort of solve that quickly can be, you have to make some sense out of all those notions, but there have been ways in which that's been done. And then maybe that, maybe now at that point, the difference becomes, perhaps more qualitative rather than quantitative. And then you get, again, some insight, which you can then apply to solving the finite problem that you're really interested in. Again, these are good ideas. None of them have led to a solution that, up until now, but hopefully somebody will solve it. I frequently get asked, do you think will ever be solved, or is there some obstacle which will prevent us from ever solving this problem? I'm an optimist. I think it will be solved someday, but maybe one of you. That's the end. So if there's any questions out there, I'm happy to take them. I don't know if I'm, so somebody's asking, is it proved or still, so it's, P versus NP is wide open. This is a very famous problem. We don't know whether there is problems like the clique problem or the factoring problem or any of those other problems. As I showed, there's a connection between many of those problems. Ultimately, like for P versus NP, it's enough just to think about the clique problem. But we don't know whether there's a fast way to solve that or whether you really need to do a brute force algorithm. Any other questions out there, folks? Andrew, is there anything you want me to take?
I don't think I see any other questions at the moment. So in that case, I guess, thank you so much for talking. If everyone could give say thank you to Professor Sipser for a great talk, as always. I'll stop the recording now.